In exercises 1 and 3, we need to use Cramer's rule to compute the solution of the system. Both of them are represented by two equations, so both of them would be 2 by 2 matrix. So for the first one, we can write it as a matrix equation which is 5, 2, 7, 4 multiplied by x1, x2, this will be equal 3, 1. So now to find x1, using the Cramer's rule, it is determinant of the matrix A, and we need to replace the first column by 3, 1. So 3, 1 is 7, 4 divided by determinant of the matrix A, which is 5, 2, 7, 4. So now the determinant of this one, 3 multiplied by 4, 12, 12 minus 7, this is 5. Then 5 multiplied by 4, 20, 20 minus 14, this will give us 6. So x1 is equal 5 over 6. Now to find x2, it is determinant of 5, 2, we need to replace the second column by b, which is 3, 1. Divided by determinant of A, which is 5, 2, 7, 4. So now determinant of this one, 5 multiplied by 1, 5. 5 minus 6, which is minus 1, divided by determinant of this one is 6. So x1 is equal 5 over 6. x2 is equal minus 1 over 6. In the same way, we do number 3. First, we write it as a matrix equation. Then we solve it for x1, for x2 using the Cramer's rule. So here our matrix A, our x and p. So now x1 will be equal determinant of the matrix A. We replace the first column by 3 minus 5. Here we have minus 2, 6. Divided by determinant of the matrix A, 3 minus 4 minus 2, 6. So now the determinant, 3 multiplied by 6, 18, minus 2 multiplied by 5, so 18 minus 10. This will give us 8 over 10, which is equal 4 over 5. Also determinant of this one, 10. So 3 multiplied by 6, minus 2 multiplied by minus 4. Now for x2, in this is the same way, 3 minus 4, replace the second column by 3 minus 5. Then determinant of the matrix A. So this will give us, this one 3 multiplied minus 5 minus 3 multiplied minus 4. This will give us minus 15 plus 12, so it will be minus 3. Determinant of this one is 10. So x1 will be 4 over 5, x2 will be minus 3 over 10. So similarly for 5, except in 5 we have a 3 by 3 matrix. So first we write the system as a matrix equation. Then we find the determinant of A. First we use one row operation, we get the determinant is equal minus 8. So to find x1, just we need to replace the first column by B divided by determinant of A. We find it is 1 over 4. Similarly for x2, we need to replace the second column of the matrix A by B and find the determinant, and also for x3. In exercise 7 to 10, determine the values of the parameter S for which the system has a unique solution and describe the solution. So we know that the system has a unique solution if this system, or if we write the matrix and the matrix is invertible, that means the determinant is not equal to 0. So now, if we do this one, first we write it as a matrix equation, so 6s, then 9, then 4, 2s. Here we have x1, x2. It is equal 5 minus 2. So now we need to find the determinant. So if we say this one is A, determinant of A is equal 6s multiplied by 2s, so this is a 12s square minus 9 multiplied by 4, this one 36. If we check 12 as a common factor, so we left with s square minus 3, sorry. So now the system has a unique solution if the determinant is not equal to 0. So if determinant of A is not equal to 0, that means we need 12 s square minus 3 not equal to 0. So from here s square not equal to 3, so s not equal plus or minus root 3. So the system has a unique solution if s is not equal plus or minus 3. Also we need to describe the solution. So we need to find what is x1, x2. So x1 will be the determinant of the matrix A. We replace the first column by 5 minus 2, here 4, 2s. Then, sorry, this one is determinant, not a matrix notation. Divided by the determinant of A, which is this one, 12 s square minus 3. Similarly, x2 is the determinant of 6s, 9, replace the second column by 5 minus 2, divide by determinant of matrix, which is 12 s square minus 3. So now let us find determinant. 5 multiplied by 2, 10s, then minus, and here we have minus, so it will be plus 8, divided by 12 s square minus 3. We can simplify this one, divide all by 2, so we'll get 5s plus 4 divided by 6s square minus 3. So for this one, 6s multiplied by minus 2, it will be minus 12s, then minus 45 divided by 12 s square minus 3. We can divide all by 3, we get minus 4s minus 15 divide by 4 s square minus 3. So in 9, similarly, we need to do the same thing, just we need to write the matrix multiplied by x is equal to b. So first we need to decide the determinant of A. So the determinant is not equal to 0, that means 6s multiplied by s minus 1 not equal to 0. So s is not equal to 0 or s not equal 1. Then to find x1, just we need to replace the first column in the matrix by p. Then find the determinant of this matrix divided over determinant of A. Similarly, the second one, to find x2, we need to replace the second column by minus 1 and 4, then we find the determinant. So this is x1 and x2. In exercises 11 to 16, compute the adjugate of the given matrix and then use theorem 8 to give the inverse of the matrix. So first, to find the adjugate, we need to find the cofactor for every entries inside this matrix. So first we need to find C11, then we need to find C12, then C13, then C21, C22, C23, then C31, C32, C33. We start by the first one is positive, then negative, then positive. Then this one is negative, positive, negative. So positive, negative, positive. So now C11, so that means we take the first one, cross this one, so just we left with the determinant of the matrix 0, 0, 1, 1. Similarly, C12, we need to cross this one, we left with the determinant of 5, minus 1, 0, 1. For C13, we left with the determinant of the matrix 5, minus 1, 0, 1. Similarly for C21, so we need to take this element, cross this one, we left with minus 2, minus 1, then 1, 1. For C22, we left with 0, minus 1, then minus 1, 1. C23, so that means we need to cross this one, so we have 0, minus 2, minus 1, and 1. Then for C31, here we have minus 2, 0, minus 1, 0. For C32, which is this one, so we cross this one, we have 0, 5, minus 1, 0. So 0, 5, minus 1, 0. Then for C33, we left with 0, minus 2, 5, 0. Now let us evaluate the determinant of this one. So this one is 0, this one is 5 minus 0, and here we have minus, so minus 5. This one is 5. For this one, minus 2 plus 1, and here we have minus, so it will be 1. For this one, 0, then here we have minus 1, and here we have plus, so it will be minus 1. For this one, it is minus 2, and here we have minus, so it will be plus 2. For this one, 0, 0, so this is 0. This one also 0, minus 5, and here we have minus, so it will be minus and minus, so here we have minus 5. Then for C33, we have this one 0, this one is minus 10, and because we have minus, so it will be also plus 10. Now for aggregate, of A, it is equal. We need to take all these elements and rearrange it. If this one is as a row, we need to write it as a column. So 0, minus 5, 5, then 1, minus 1, 2, then 0, minus 5, and 10. So this is the aggregate of A. Now to find the A inverse, first we need to find what is the determinant of A. To find determinant of A, let us take aggregate of A multiplied by A. This will give us 0, minus 5, and 5, 1, minus 1, and 2. Then 0, minus 5, and 10. We multiply by the matrix A, which is 0, 5, minus 1, minus 2, 0, 1, minus 1, 0, 1. After you multiply the aggregate of A by A, we finally reach to the matrix, which is 5, 0, 0, 0, 5, 0, 0, 0, 5. This one is just 5 multiplied by I3. So from here we conclude that determinant of A is equal to 5. Because if we multiply the aggregate of A by A, we get the determinant of A multiplied by the identity matrix. So from here it is 5I3, so this one represents the determinant of A. So now A inverse will be equal 1 over 5 multiplied by aggregate of A, which is 0, minus 5, and 5, 1, minus 1, and 2, 0, minus 5, and 10. So this is our A inverse using the aggregate of A and theorem 8. For 13 we need to do similar as we did in 11. We need to find the adjugate, then we need to find the inverse using theorem 8, which is tell us that the inverse of A is equal the adjugate of A multiplied by 1 over 5, multiplied by 1 over determinant of A. So first we find all these cofactors, then after that we rewrite it, or we rearrange it to write the adjugate of A. So this one as a row, we write it here as a column. This one also as row, we write it as a column, and similarly for the last one. Then we multiply adjugate of A by A, we get this matrix. You have to get similar like this one, which is constant multiplied by the identity. If you didn't get this one, that means you did something wrong in your matrix, the adjugate of A. So you have to rewrite it or to refind it again. So once you find this one, so from here you conclude that the determinant of A is equal to this number, which is 6. Then finally A inverse will be adjugate of A divided by the determinant of the matrix A. Similarly in 15, first we find cofactor for each element inside this matrix. Find the adjugate of A. We multiply adjugate of A multiplied by A, we get this 4. So from here we conclude that determinant of A is equal, minus 5, and so A inverse is equal 1 over, this one is minus 5, so it will be minus 1 over 5, and we multiply by the adjugate of A. So this is our A inverse. In exercise 18, suppose that all the entries in A are integers and determinant of A is equal 1. Explain why all the entries in A inverse are integers. Since all the entries in A are integers, so that means all the factors should be also an integers. So let us write here, each cofactor of A is an integer since it is a sum of an integer. So since it is a sum of product of entries in A. So every cofactor will be integers because each element or each entry in A is an integer. Now, since all the cofactor of A is an integer, that means each entry in adjugate of A will be an integer. So each entries in adjugate of A is an integer. And we are given that since determinant of A is equal to 1 and A inverse is equal 1 over determinant of A, adjugate of A, that means the inverse A inverse show that all entries in A inverse will be also an integer. This one is only 1, so it will be just adjugate of A. So every element in A inverse will be just the entries in the adjugate of A. And we know that every entries in the adjugate of A is an integer, so that means A inverse consists only of integer values. So hence all entries in A inverse will be integers. In exercise 21, we need to find the area of the parallelogram whose vertices are listed. So we have parallelogram whose vertices, these 4 vertices. First, as we did in examples, we need to put one of these points as 0, 0. So if we want to make this one to be the first one to be 0, 0, that means we need to add the point 2, 0. So if we add 2, 0 for the first point, we need to add it for all the others. So minus 2, 0, if we add it with 2, 0, we get the point 0, 0. So since we add 2, 0 to the first point, we need to add it to the second point also. So plus 2, 0, then similarly 1, 3 plus 2, 0, then the last one minus 1, 0 plus 2, 0. So now this will give us 0 plus 2, 2, this one 3, then 3 and 3, last one is 1 and 0. So now we have 3 points and one of them 3 points and the fourth one is the origin point. So if we see this point, if we say this one, let us A, P, C, D. We see that the point B plus the point D, so B plus D will give us the point C, because B is 2, 3, D is 1, 0. If we add 2 plus 1 will give us a 3, 3 plus 0 will give us a 3. So B plus D will be equal to C. So we know that this parallelogram is, the parallelogram has the points that correspond to this parallelogram will be the 2 vectors which is correspond to P and D. So this parallelogram is determined by, so the parallelogram is determined by P and D. If we write it as a matrix, so i.e. our matrix A, B is just 0, 3, D is 1, 0. B is 2, 3, sorry. Two, 3, and then D 1, 0. So now we know that the area is given by, so the area is equal the determinant of A, which is equal to multiplied by 0 minus 3 multiplied by 1, and we know that we need to take the absolute value of this one because it is an area, so it will be 0, this one 0 minus 3 will give us absolute value of minus 3, which is equal to 3. For this you can make this one to be 0 by adding minus 0 minus 3, or you may take this one to be 0, so you add minus 1 and minus 3, or you may take this one to be 0, you add 1 and 0. You should take only this one. You have to choose whatever feel you easy for you. So take any points and make it first 0. Then you will find that 2, if you add 2 points, you will find the fourth one. So one of them will be 0. 2 of them, if you add it, you will get the fourth one. So these two, when you add it and you get the fourth one, that means your parallelogram can be determined by these 2 points. So just you need to consist the matrix A, and then you find the determinant of A, and take the absolute value, and this will represent the area of the parallelogram. In 29, find a formula for the area of the triangle whose vertices are 0, V1 and V2 in R2. For example, if we have this one, so for example this one is V1, this one is V2, and here we have the point 0, 0, so the parallelogram will be this one. We need to find the area of the triangle whose vertices are 0, 0, V1, so we need to find this area. We know this area is just half the area of the parallelogram, and the area of the parallelogram, so the area of the triangle, is equal half the area of the parallelogram, which is equal half. We know that the area of the parallelogram, it is the determinant of A. If A is equal V1, V2, then so the area of the triangle will be half the area of the parallelogram, which is half absolute value determinant of A. So the area of the triangle will be half determinant of the absolute value of the determinant of the matrix A.